Okay, so our matrix equation for number 111 yields this augmented matrix, the solutions of which will be our values of C1, C2, and C3. Now, maybe the reduction leads you to an identity matrix with, of course, 3 numbers over here. If you get an identity matrix over here, you will have 3 numbers over here. It could all be 0, but they probably aren't. Well, in some situations, actually, you expect that they would be. And this matrix would then correspond to C1 equals whatever this number is. And remember, asterisks stand for numbers that, even though I'm using asterisks for all 3 of these numbers, no asterisk has to equal any other. So I've got these 3 asterisks here. So C1 is the first asterisk, C2 is the second, C3 is the third. Whatever comes out when we reduce this, those will be our 3 numbers. And those will be our values of C1, C2, C3. So we know that we can add a multiple of this vector to a multiple of this vector and a multiple of this vector to get this vector. Okay? And we know what those numbers are, and we also know that that's unique. The C1, C2, and C3 have to have these 3 values. They don't have any other values. Okay, so this would give us a unique C1, C2, C3 that says that we can actually do this. Now, we can't necessarily always do this, though. So, maybe. So what I said here is it could come out like this, or it could come out worse. Well, there are a lot of ways it could come out. Okay, one way might be 1, 0, 0, asterisk, 0, 1, 0, asterisk, and 0, 0, 0, double asterisk. And actually, if you got a 0 here, chances are you're going to have an asterisk here and here, and that doesn't change anything. Okay? So, what does this mean? Well, 0, okay, double asterisk means non-zero. So that means it ain't 0. So what does this give us? This gives us 0 equals something that ain't 0. Okay, well, that isn't supposed to happen. And do I have room down there? Yeah, I do. Okay. So this can't be. So no way. So no solution. What does it mean that there's no solution? It means you can't find a C1, a C2, and a C3 that add up to this. Okay? Now we're going to leave it at that for the moment. There's geometric interpretations of this, but we'll get into those in Chapter 4 when we start studying vector spaces. Okay, so here we have it. And there are other forms that this matrix could take. For example, if it was 0, 0, 0, 0, if this was 0, then you can't say there's no solution. You'd have 0 equals 0. That's perfectly okay. That means that your z, what y plus z is some number and x plus z is some number. That means you can parameterize the solution in a way that shows that there are infinitely many combinations of C1, C2, and C3 that would add up to this vector. Okay, so it doesn't mean you can choose just any combination. It has to be a combination with z equals 0, and then it's going to turn out that y equals this asterisk and x equals, oh, wait a minute. No, you get z 0 equals 0. It doesn't tell you that z equals 0. I stopped thinking there for a minute apparently. Okay, 0 equals 0 means that z could be any value. So you put any value here and the same value here, and you get two equations. Now, maybe amplifying that idea because we didn't talk a lot about how things parameterize. And you had a couple of problems on it that we were busy learning to row reduce and translate things. Okay, so anyhow, that's this. Now this is a very, very important situation. When you get to vector spaces, you will see why it's important, and you'll see that it's important. Until then, just know how to set it up, because then you won't have to stumble over setting it up when you have to do it later in a meaningful context.